All right, welcome back to part 2 of L'Hopital's rule. We get into some extra rules here today. There's the infinity minus infinity or infinity times 0 case. I know these are two separate indeterminate forms here, infinity minus infinity or infinity times 0, but really they end up looking the same way once you apply L'Hopital's rule, so I kind of build them into one. So infinity minus infinity is an indeterminate form because these don't have to be the same infinities. They can be two giant numbers that when you subtract them don't actually get you 0. They might get you 5, or they might get you 0, or they might get you infinity back. Because what if this first infinity is way bigger than the second? Infinity times 0 is also an indeterminate case because if I have a giant number times a teeny tiny number, it might stay giant, or if the teeny tiny number is so close to 0 it brings it down to 0. They might in some way cancel out and give you like 7 or a half. We don't know. So these are both indeterminate forms, all right? So if you get either of these two forms, then you rearrange the original expression so you can get infinity over infinity or 0 over 0. And then once you do that, you can use L'Hopital again. So we're still kind of going back to that original fractional form of L'Hopital. We just have to do a little bit of rearranging. So let me show you what that looks like. If I have the limit as x approaches 0 of cosecant x times ln x plus 1, if I were to like plug in 0, cosecant x is like 1 over the sine of 0 times the ln of 1. Well, 1 over sine 0 is kind of like 1 over 0. ln 1 is 0, so this is kind of like infinity times 0, which is indeterminate. So what I'm going to do is I'm going to rewrite this and say, you know what? Another way to do this is the limit as x approaches 0 from the right of 1 over sine x times ln x plus 1, which becomes ln x plus 1 over sine x. Now when I plug in that 0, I get ln 1 over 0, which is 0 over 0. So now I can use L'Hopital. So I'm going to use L'Hopital and take the derivative of the top and the derivative of the bottom. So I'm going to get 1 over x plus 1 on top over cosine x on the bottom. And now I'm going to plug in 0 again, which gives me 1 over 1 on top, and the cosine of 0, which is 1 on the bottom. So I get 1. So here's a crazy way where infinity times 0 is actually kind of 1. But again, you need to understand, it's not infinity times 0. It's a very, very large number times a very, very small number. And you're trying to see what happens after that. All right, example 2, x times ln x. So if I were to plug in 0, this would end up being 0 times the ln of 0 from the right. So if I think of the graph of ln x, it looks something like that. To the right of 0, this is headed towards negative infinity. So this is a 0 times infinity case. So I am going to rewrite this as a fraction. Well, how am I going to do that? I'm going to be a little creative here and say, you know what? I can rewrite this as ln x over 1 over x. That would be exactly equivalent to this first thing. So I can absolutely do this because they are equivalent expressions. Now when I plug in 0, I get negative infinity on top, and 1 over 0 on the bottom is like positive infinity. This is a L'Hopital form. So now I'm going to use L'Hopital. I'm going to take the derivative of the top and of the bottom. Derivative of ln x is 1 over x. The derivative of 1 over x is negative 1 over x squared. I'm going to simplify that, so that's like the limit as x approaches 0 of 1 over x times negative x squared over 1, which is the limit as x approaches 0, forgot to put my little plus there, of negative x. Well, the limit as x approaches 0 of negative x is 0. So here's a crazy case where infinity divided by infinity is 0. All right, coming down here, the limit as x approaches 0 from the left of 1 over sine x minus 1 over x. So this is going to be, let's see, 1 over sine x is like 1 over 0. 1 over x is also like 1 over 0. 1 over 0 is like infinity minus infinity. Now technically I'm coming at 0 from the left, so the sine of 0 from the left is like 1 divided by a negative 0, which would give me a negative infinity, and 1 divided by 0 from the left here, well, x coming at 0 from the left would be negative also, which makes this another negative infinity. So it's really like negative infinity plus infinity. but that's the same as infinity minus infinity. So you don't have to worry about it, but I wanted to take a point of saying this is 0 from the left, technically. Now, this case, I've got infinity minus infinity with two fractions. I just want to turn them into one fraction. Well, that's easy enough. I'm just going to make a common denominator. So I have 0 from the left now of x minus sine x over x sine x. If I were to give these a common denominator, the first one get multiplied by x over x, the second by sine x over sine x, which gives me x minus sine x over x sine x. Now let's see if this is a L'Hopital form here. I'd have 0 minus 0 over 0 times 0, which is 0 over 0. So yay, I get to use L'Hopital. So I'm going to take the limit as x approaches 0 from the, not the right, 0 from the left, pardon me. The limit as x approaches 0 from the left of the derivative of the top over the derivative of the bottom, which is a product rule. So the first times the derivative of the second plus the second times the derivative of the first. Now I'm going to plug in 0, which is going to get me 1 minus 1 over 0 plus 0. Oh, shucks. I got 0 over 0 again. That's okay. I can do L'Hopital again. Woohoo! So now I'm going to take the limit as x approaches 0 from the left of the derivative of the top, which would be sine x, over the derivative of the bottom, which is a product rule again. So the first times the derivative of the second, plus the second times the derivative of the first, plus the derivative of sine x, which is cosine x. I'm going to plug in 0 again, so I have 0 over 0 plus 1 plus 1. Well, that's 0. And there's my limit. If you're feeling pretty comfortable, try and do example 4 on your own. So hit pause, then come back. Welcome back. If we take the limit as x approaches 1 here, I have 1 over ln 1 minus 1 over 1 minus 1, which is like 1 over 0 minus 1 over 0, which is like infinity, whoa, minus infinity. So in this one, I'm going to do the same thing I did before. I'm going to try to make it one fraction. So I'm going to have x minus 1 minus ln x over ln x times x minus 1. If I plug in 1 now, I have 1 minus 1 minus 0 over 0 times 0, which is 0 over 0, which is a L'Hopital form. I'm going to take the derivative of the top and of the bottom, which is going to be 1 minus 1 over x, divided by a product rule, so I have the first times the derivative of the second, minus the second times the derivative of the first. I'm not too thrilled about those complex fractions, so I'm going to go through and simplify this real quick and make it the limit as x approaches 1 of x minus 1 over x ln x minus x minus 1. What did I do to get from here to here? I just multiplied my numerator and my denominator both by x. I should probably put fraction parentheses there. So I multiplied the numerator and the denominator by x to get rid of the complex fraction. Now if I plug in 1 for x, I get 1 minus 1 over 1 times 0 minus 0. Oh, it's 0 over 0 again. That's okay. I can use L'Hopital again. So now I'm going to use this form. Take the derivative of the top and of the bottom. So the derivative of the top is going to be 1. The derivative of the bottom is a product rule. The first times the derivative of the second, plus the second times the derivative of the first, minus 1. So this is going to be the limit. Oh, what just happened there? Nope, things are moving. Let's try this again. Sorry about that. The limit as x approaches 1 of 1 over 1 plus ln x minus 1, which is going to be 1 over 1 plus 0 minus 1, which is 1 over 0. Well, wait, that's not a L'Hopital form. Can I do L'Hopital again to get rid of it? No. Is 1 divided by 0 something? Well, not really. Let's see. You know what, guys? Mrs. Vibber made a mistake somewhere, didn't I? When I came up here and I did the product rule, this was supposed to be a plus. I knew I wasn't supposed to get that. So this is a plus, which makes that a plus, which makes this a plus, which makes that a plus. Wait a minute. It's 1/2. There we go. This is a teachable moment, though. So Mrs. Vibber made a mistake. So I went back, I fixed my mistake. Yay, 1/2, I'm all set. Let's say for a second that it wasn't a mistake, and I ended up with 1/0 as a final quote-unquote limit. That would mean that you now get to say the limit does not exist. If you ever end up with a non-L'Hopital form, but you do have a 0 on the bottom, you can say the limit does not exist, and just leave it at that. However, in this case, it did exist. It equals 1/2. This is just me being a nincompoop and losing a positive sign and making it a negative. All right, so 1/2, there we go. Moving on. If you want to see that without the mistake, you can look at my answer key and just follow it through from there, that PDF form that I have. All right, now we get into the nitty-gritty stuff, and it's so much fun because it has logarithms. All right, so if we have a 1 to the infinity or a 0 to a 0, that's another indeterminate form. Reason being 1 to the infinity is indeterminate because if it's slightly less than 1 to the infinity, it's going to go towards 0. Slightly more than 1 to infinity is going to get very, very large. 0 to the 0 is also indeterminate because is it 0? Is it 1? Is it something in between? We don't know. So if you get either of these two indeterminate forms, what we need to do is basically take it away from being exponential and make it a fraction. What we do to do that is we set the limit equal to L, and then we take the ln of both sides. Because if I can take the ln of both sides, I can bring down the exponent using log laws. Then you have a different indeterminate form. You rearrange it to get a fraction. Then you get to do L'Hopital's rule. And then at the very end, the value of the limit is set equal to ln L. So then you have to solve for L. So none of that's going to make sense till we do an example here. So the limit as x approaches infinity of 1 plus 1 over x to the x. Well, if I plug in infinity, this is going to be 1 plus 1 over infinity to the infinity, which is like 1 plus 0 to the infinity, which is like 1 to the infinity. That's indeterminate. So what we do is this. I have the limit as x approaches infinity of 1 plus 1 over x to the x. I'm going to say, you know what? That limit has a value. That value is equal to L. Well, now I'm going to take the ln of both sides. So I am going to move my limit out in front. So I have the limit as x approaches infinity of ln 1 plus 1 over x to the x equals the ln of L. Well, using log laws, this x can come down in front. And now I have that. And now, if I look at the limit as x approaches infinity, I have infinity times the ln of 1 plus 1 over x, which is like infinity times ln 1, which is infinity times 0. That's an indeterminate form. So I'm going to turn this into a fraction. So I'm going to take the limit as x approaches infinity of ln 1 plus 1 over x divided by 1 over x. This is equal to that, and it's still equal to ln L. Now if I plug in infinity, I have ln 1, which is 0, over 1 over infinity, which is 0. This is like a 0 over 0 form, which means I get to do L'Hopital to the top and the bottom. Now, I'm running out of room here, so you know what? I'm going to move off to the side. So this is going to come over here. I'm just giving myself more room. So I have the limit as x approaches infinity of the derivative of the top. Oh, well, the derivative of an ln is the derivative of the end over the end. So that's going to be negative 1 over x squared over 1 plus 1 over x. And then the derivative of 1 over x is negative 1 over x squared. This is still set equal to ln L. And what happens here is actually this cancels with that and leaves a 1 behind. So this just simplifies down to 1 over 1 plus 1 over x equals ln L. Now when I plug in infinity, I have 1 over 1 plus 1 over infinity, which is like 1 over 1 plus 0, which is 1. That's set equal to ln L. Well, if 1 equals ln L, then L equals e to the 1, and L equals e. Okay, What on earth just happened, Mrs. Vibber? You just did a lot of stuff. Okay, so let me backtrack. I had a limit that I didn't know how to evaluate. I plugged in infinity, got 1 to the infinity, and said, hey, that's an indeterminate form. So I said, all right, if it's an indeterminate form and it's an exponential indeterminate, you're going to set it equal to L. That allows me to take the ln of both sides. The reason I want to do that is because then I can bring this power down, and now I have the limit of a product. Well, this product became infinity times the ln of 1, which is like infinity times 0, which is a different indeterminate form that I then created a fraction out of. So I said x times ln of 1 plus 1 over x is like the ln of 1 plus 1 over x divided by 1 over x. Still set equal to ln L. I plug infinity into this guy. I get ln 1 over 0, which is 0 over 0. So then I can do L'Hopital and take the derivative of the top and the bottom. I did that. I simplified. I got this. I plugged in the infinity, got 1, said, wait, that 1 still said equal to ln L, solved for L, and got E. Okay, here's another important thing on this one. On this one, what we just learned is that the limit as x approaches infinity of 1 plus 1 over x, what is happening right here, to the x, is equal to E. This is something that you should kind of try to remember. One definition of E is this limit right here. All right, one more and then we're done. Limit as x approaches 0 of x to the x. Well, if I plug 0 in there, I have 0 to the 0. This is indeterminate. So I'm going to take my original limit. I'm going to set it equal to L. I'm going to take the ln of both sides. Because, you know, why not? Then I'm going to use that to bring down this exponent. Now I'm going to plug 0 in again. 0 times ln 0. Well, ln of 0 doesn't exist, but this isn't really 0. It's technically, you know, kind of 0. The ln of kind of 0 is negative infinity. 0 times negative infinity is indeterminate, so I'm going to turn this into a fraction. The limit as x approaches 0 of ln x divided by 1 over x equals ln L. I'm going to plug in 0 again. I'm going to get infinity on top. 1 over 0 is infinity on the bottom. Now I can do L'Hopital. So right here I created a fraction. Whoops, sorry about that. Right here I'm about to do L'Hopital. All right, if I do L'Hopital down here, I take the derivative of the numerator and denominator. I get 1 over x for my numerator. I get negative 1 over x squared for my denominator. Still set equal to ln L. If I simplify, this becomes negative x, and the limit as x approaches 0 of negative x is 0. But that's set equal to ln L. If I solve for L, I get e to the 0, which is 1, which means the limit as x approaches 0 of x to the x is 1. All right, I know that was crazy. We'll go over it again in class. But long story short, if you have infinity minus infinity, or what was the other one? Infinity times 0, what you want to do is create a fraction and then do L'Hopital. If you have an exponential indeterminate form, like 0 to the 0, or 1 to the infinity, you want to set it equal to L, take the ln of both sides, and then solve for L. All right, come to class tomorrow ready to work and be psyched because we have logarithms. I will see you in class. Good luck.